This is a quick review of the fundamental theorem of calculus. We have this page from your textbook, 1135, that talks about the different kinds of fundamental theorem calculus. There's this one from Calc 2, which we won't use. Well, we kind of will when you guys have to compute integrals. But this is the original fundamental theorem of calculus. The new fundamental theorems that we have is the fundamental theorem of line integrals, Green's, Stokes' divergence theorem that comes in two forms, one on the plane and this one that's given here is in space. So sometimes it's called Gauss. So what I wanted to do is just take a look at some problems from the review and see how to approach it. So the first set of problems I want to look at are number 13 and 14. This is on page 1137 in your textbook. So if you look at the problems that we have, we are given a vector field and a curve, and the curve is some open curve. So we have to show that it's conservative, and there are several ways to do that. One way is to take the curl of it, and remember in two dimensions, if we're doing the curl, we just have one component. So in 2D, the curl is really just equal to the derivative of q with respect to x minus the derivative of p with respect to y, and this is going to just happen in one component. So all you really need to do is find this curl. To find the curl is to find this difference. If it's equal to 0, it's conservative. The other way to find it is something that you'll need to do anyways. If you find that this is equal to 0 and is conservative, to be able to actually solve or find this line integral, you would find the potential. And the potential is when you take the antiderivative and well, this is what you're given. You take the antiderivative to find the original little f, which is saying that the big F is a gradient of little f. And so once you do that, you really just compute the endpoints, use the fundamental theorem of line integrals, and then evaluate at the endpoints. And you find the endpoints by putting in those values. In some cases like this, they give you the actual endpoints, and so this is a three-dimensional equivalent of problem number 13. So this uses the fundamental theorem of line integrals. And you should actually go ahead and compute this in while you're reviewing. Alright, the next set of problems I want to do is Green's theorem problems, and although in these problems they actually explicitly tell you to use Green's theorem, I think it's still worth looking at why you would be using Green's theorem. So what are the key features of these problems? Well, this one, a lot of Green's theorem problems, they write your line integral, instead of writing your line integral like this, they write it like this. So this is not the only reason why you would think about using Green's theorem. However, that's usually a big clue that your line integral is split up into the dx and dy components. and then that kind of moves into that formula where Green's theorem's formula is written like this. The other big key for Green's theorem is looking at C. And C is usually closed. So, like for this example over here, C consists of the parabola y is equal to x squared from minus 1, 1 to 1, 1, then a line segment going this way. So this is our curve, and clearly it's closed, and it encloses a fairly simple region that you can do a double integral on. And that's what happens with Green's theorem, is that you're going to replace this line integral for a double integral. Here's another one. Consists of a triangle from 0, 0, 1, 0, and 1, 3. So again, fairly simple region to do a double integral on. You need to find the equation of this line. And then this becomes an easy double integral after you take the curl of this. And then the last one, the obvious one, is here we have a circle at radius 2 with a counterclockwise orientation. And so this looks like another candidate for Green's theorem. All these Green's theorem curves in 2 dimensions are all closed, and so they enclose a space that hopefully would be easy to do a double integral on. Moving along. Down over here we got a bunch of Stokes theorem problems. Most of the problems will, they tell you to use Stokes theorem. But the key is that for Stokes theorem you need to find the flux of the curl. If you're not just verifying, you're looking for the flux of the curl, and so whenever you see that, then you got to be thinking Stokes. And now when you're thinking Stokes, you have to look at the surface that they're giving you. It says here the surface, this is the whole sphere, x squared plus y squared plus z squared is equal to 5, so this has a radius of square root of 5. That lies above the plane z is equal to 1, so this even gets cut off. Z is equal to 1. And so what we have left here is part of the sphere that's been cut off over here. And so this is going to be your boundary. So you're going to trade in the flux integral for a line integral over this boundary. And so what you need to do is you need to know how this boundary, be able to describe this boundary and know how it looks like. For these ones that use this one, it says use Stokes theorem. This time they give you the line integral, and so this time you're gonna change it into a flux integral. So let's see how to approach this one. We have a line integral, and they give us the vector field, and so the triangle has vertices at 1, 0, 0, 0, 0, 1, 0, and 0, 0, 1. So here's your triangle. I think this has an orientation that looks like this. So what we could do is we can find the equation of this plane. and this is in fact just a plane. And so we can trade in your line integral with a double integral of the curl of f ds over this surface with that specific boundary. So this becomes a surface integral, which will, after you parameterize this plane, will become a double integral. This plane, by the way, is x plus y plus z is equal to 1. We've had tetrahedron problems that kind of have this shape, and so this obviously isn't a tetrahedron because it's not a whole solid, but we're just looking at the top part of the plane there. And so we have a plane that looks like this, so you can parameterize it using just a regular graph parameterization, x, y, and then that would have the x for the x component, and then the y for the y component, and then a z for the z component will be the plane itself. So that's in terms of x and y. And then your domain is going to be basically whatever this is going to look like on the xy plane, the shadow on the xy plane. So it crossed the x-axis at 1, it crossed the y-axis at 1, and then the z is going to cross wherever it's going to cross, but this is going to be your domain. So this curl of f, what you need to do is you need to plug in this parameterization after you take the curl of it, and then after you do the parameterization you integrate over this thing. So this is going to become a double integral over this domain D. And then you take the curl of f and then you evaluate it at this parameterization. So the curl of f is just another vector field. So you evaluate that parameterization and then you dot it with a normal vector. A normal vector would be coming out this way. You can also figure that out eventually based on your parameterization. And one way to do that is find the normal vectors. So, and then the surface integral after you do this application is going to become just a dA for the double integral. Alright, so verifying Stokes' theorem just tells you to relate your curl with your line integral. And then make sure that they're equal. So in the test situation, I probably won't ask you to verify, but you'll probably be doing one of these two. The last type of fundamental theorem of calculus problem would be using Gauss. So I'll probably refer to it as Gauss, but if you see the divergence theorem, that's the same thing. So in these ones, what kinds of integrals are we actually looking at? We are looking at regular flux integrals, not the flux of the curl, but just the flux of f. And then usually we're looking at a solid bounded by some surfaces, or surface, a surface. So in this case we have the flux of f, and then our boundary, or our surface S, is a surface bounded by the cylinders, or the cylinder, from 0 to 2, and then this has a radius 1. So the other thing for these divergence theorem problems, for the Gauss problems, is that you need to take the div of f and then put that into the triple integral, where the solid that you're integrating over is the inside of the surface. So usually the surface is closed, and if it's not closed you may have to close it, if you're feeling like you really need to use Gauss. And again, the flux integral of f, not the curl of f, just f. And then the other part is that when you take the div of a problem, it looks like you might simplify things. So the div of this is 3x plus, or 3x squared plus 3y squared plus 3z squared. Now at first glance this might not be so easy looking, but you got x squared plus y squared plus z squared, and so maybe in this particular case, because we have a cylinder, we might just go to cylindrical coordinates, which is still going to simplify this quite a bit. But if it's a sphere, then this would definitely be an easier integral, because you can replace x squared plus y squared plus z squared with rho squared. Okay. Yeah, so a lot of times your vector field for these Gauss theorem problems would be nice vector fields, or easier vector fields that you could take the div of, and when you take the div of this, things turn out to be nice and easy. So that would be another clue that you're going to be using Gauss. And so just a couple more looks at a couple more things. Just by looking without reading too much, I'm looking at this curve over here that you would be integrating over. This is number 37. And as I do that, I almost kind of ignored everything else and just imagined the starting and ending points for this. So for this kind of problem, it looks like I might be using the fundamental theorem of line integrals. So I have a start end, so I'm hoping that this is actually a conservative vector field, and I would find its potential function. So from here we would find little f, where the gradient of little f is equal to the vector field. So I would probably use the first fundamental theorem there. And then one more problem to look at. By the way, this one, number 38, I would probably be thinking about using Green's theorem. It's a closed curve, and then we have an area, although finding the area double integral there looks like it might be difficult. But I wanted to look at number 39. So this one is a good candidate probably for Gauss. It's asking us for the flux of the vector field, not the flux of the curl, but the original vector field. I look at this vector field, the div is going to be really easy to compute. And then I look at this surface. This has it's a cube, so it has 6 sides, but we added in 3 more sides, so now we have 9 sides. So finding the flux over each of those surfaces would be kind of difficult. But now if you look at this as a solid, this is a cube with a smaller cube taken out of it, so it all of a sudden becomes an easier problem if you're using Gauss, especially when the div of f is a constant. So your triple integral will just be looking at the volume of whatever figure you're looking at. So okay, so I think those are my hints for using the fundamental theorem calculus. Good luck.